I'm going to talk about non-continuous graphs. And when I say non-continuous, what I mean is there's a break. And where the break is, that's called a point of discontinuity. And a graph is continuous if there's no jump, break, or holes. You can draw the graph and your pencil never leaves the paper. So if I did this test on this graph here, you notice that I'm tracing, but my pen goes up and then I continue to trace. So you know that there is a point of discontinuity. In other words, there's a break. This type of discontinuity is removable. Why is it removable? Because you can define an answer at that point. A discontinuity that is non-removable there literally is an asymptote and a horizontal asymptote. So there's no replacing of that at that point. It's discontinuous. Okay? So we're going to be talking about those type of discontinuities or discontinuous graphs. So we're going to go ahead and go to number 1. Example 1. What are the domain points of discontinuity of each rational function? Are the points of discontinuity removable or non-removable? What are the x and y intercepts? So you notice that we have y equals x plus 3 over x squared minus 4x plus 3. We're going to go ahead and find the factors of the numerator. We have x squared minus 4x plus 3, get the factors of 3, which are negative 3 and negative 1. So we know that when this parentheses is equal to 0, then we know that the denominator is equal to 0. And that's where it says x minus 3 equals 0. So x equals 3. This parentheses, we have x minus 1. And when the denominator is equal to 0, x minus 1 is also equal to 0. So if x minus 1 is equal to 0, then the denominator is equal to 0. So when is it going to be 0? It's when x is equal to 1. So the domain of the function is all real numbers except for 3 and 1. There are non-removable points of discontinuity at x equal 1 and x equal 3. The x-intercept occurs when the numerator equals 0. When the numerator equals 0. So it's going to be x equals, we have negative 3 because we have x plus 3 equals 0. So x equals negative 3. This is the numerator. The y-intercept is when x equals 0. And you notice we've substituted x for 0. And it comes out to be 1. So the y-intercept. I went ahead and graphed the function x plus 3 divided by x squared minus 4x plus 3. And you notice at x equal 1, we do have a vertical asymptote. And we also have a vertical asymptote at x minus 1. How do I know? Because it's undefined there. Now, if you wanted to look at the table, you see how at x equal 1 it's undefined, and at 3 it's undefined. Okay, so, and we also see that the y-intercept is at 0, 1. So we go up at 0, 1. So we have x minus 5 divided by x squared plus 1. And you notice that if I were to trace this graph, which I am, you see the hand never jumps up or never stops. So this is actually a continuous graph. And it says here you cannot factor the numerator or the denominator. Also, there are no values to make the denominator 0. The domain for the function is all real numbers. Now, the X-Intercept is where the numerator equals to 0. So the X-Intercept is when it's 5. So we have 5 minus 5. It's going to be 0. So it's going to be the X-Intercept is 5. So we have X minus 5 equals 0. So X equals 5. The other one, it says to find the intercept is when you let X equal 0. So you have Y. You have 0 minus 5 divided by 0 squared plus 1. So you have negative 5 over 1, so it's negative 5. So the y-intercept is 0, negative 5. And you can see that the y-intercept is negative 5. Now you want to see the x-intercept, go ahead and press tab, and we're going to say x equals 0, y equals 0, and we're going to find the intersection. So we go to menu, analyze graph, find the intersection. And there is the intersection. The intersection is 5, 0, as I told you. Problem 2, we're trying to find the vertical asymptotes. What are the vertical asymptotes for each graph? What is the domain for each function? How do the vertical asymptotes relate to the domain? Since 2 and 3 are zeros in the denominator, neither is a 0 in the numerator. The lines x equals 2 and x equals 3 are the vertical asymptotes. And you can see that x equal 2 and x equal 3. So the domain of the function consists of all real numbers except the discontinuities, and the set notation of the domain is all numbers except 2 and 3. So you can write down all numbers except 2 and 3. So all the numbers less than 2, in between 2 and 3, and greater than 3 are going to be in the domain. Okay, we're going to try to find the vertical asymptote. And we know that at x equals 4, it's undefined. And we know that x cannot equal negative 3. So our vertical asymptote definitely is at 4. And you can see that here. I just graphed it. We have 1, 2, 3, 4. So our vertical asymptote is 4. Now you might be wondering, why don't we have a vertical asymptote at negative 3? Well, here's the thing. If you notice, x plus 3 divided by x plus 3 is actually 1. And when we simplify this, but if we look at our table and we go to negative 3, we know that at x equals 3, it's undefined. This is called the removable discontinuity. Why? Because you see the numerator and denominator, that would be 1 if we were to divide it. Now this one right here is a non-removable. It's non-removable because there's actually a break. There's actually a break in the graph. Since 4 is a 0 of the denominator and is not a 0 of the numerator, the line 4 is a vertical asymptote. However, while negative 3 is a 0 in the denominator, it's also a 0 in the numerator. So you want to underline that. However, while negative 3 is a 0 in the denominator, it's also a 0 for the numerator. So negative 3 corresponds to a removable discontinuity and not a vertical asymptote. Now you still say the domain will not be 4 nor negative 3, but you need to understand that there's only one vertical asymptote and the other one is a removable discontinuity. It's like just a hole. Okay, there would just be a hole on the graph. We're going to find the horizontal asymptote. Okay, and to find the horizontal asymptote, what you have to do is you have to compare your numerator and your denominator. And you notice that we have 2x here and we have x here. So all we have to do is 2x over x. And you notice that 2x divided by x is 2. As long as it's the same exponent or the same degree, it's going to be 2x over x, which is 2. So if you look over here, if I were to press tab and we say y equals 2, you notice that is our horizontal asymptote. It's right at 2. Our vertical asymptote is when it's x equals 3. It's the one that's going up or down. So if we're here, the range will be all numbers except for 2. The range, all numbers except for 2. So it's going to be all reals except 2. And how do we figure it out? Well, we have 2x and we have x. You take the two highest leading terms, divide it, and if you get a number like this, 2, then that will be your horizontal asymptote. So if you look at b, the highest exponent is 1, the highest exponent is 2, and since 2 is larger than 1, we know that the denominator is larger than the numerator, the leading term. So your horizontal asymptote will always be y equals 0. The degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is y equals 0. That's always true. Okay, and we wanted to check that. We can graph it. So I'm going to go to tab, and I'm going to go ahead and delete this. Control division. So we have x minus 2. And then in the denominator, you have x squared minus 2x minus 3. Enter. And you notice you can see our vertical asymptotes. One of them is at x equal -1, and we have x equals 3, but the horizontal asymptote, if I were to go to tab, you know that it would have to be 0, and you can see that here. You see the 0? So that's true. It says here, what is a graph of the rational function? We're going to look for our horizontal asymptote, and you notice that we have x squared and x squared. So if I were to write x squared divided by x squared, our coefficient is 1, 1. You know that the x squareds cancel, so we have at our horizontal asymptote will be at y equals 1. Our vertical asymptotes are going to be at x plus 2 equals 0 or x minus 2 equals 0. And we know that x equals 2 is a vertical asymptote, and x equals, actually that's -2, x equal 2 is a vertical asymptote. Now you want to know where is our x-intercept, and all we have to do is make the numerator equal to 0. So we know that we have x plus 4 equals 0, so we know that when x is -4, the numerator is equal to 0, and that's where you have -4 is 0. Also, when you have x minus 3 equal to 0, x equals 3 is going to also make it equal to 0, your y-intercepts. So your y-intercepts equal -4, 0. Your x-intercepts are -4, 0, 3, 0. Your y-intercept, all you have to do is replace the x with 0. So you have 4 times -3 is -12. So it's -12 divided by -4, which gives us 3. Well, that's how you got 3. So here are the vertical asymptotes. We have one at x equals 2, x equals -2, and of course we have the different points that gives us the x-intercept and also give us a y-intercept. And so the only thing I want you to remember is how to identify the horizontal asymptote, how to identify the vertical asymptote. We're going to